So we are explaining we are talking about the chapter 9, which is Euler's formula in Platonic solids. We have explained some what are the Platonic solids, and then give few examples, and then try to give the rules for, like, try to give an example for the Euler's formula, and now we will present the Euler's formula and prove it. So we give the theorem. 9.1. It says that for a convex polyhedron with V vertices, E edges, and F faces, we have vertices minus edges plus faces is always equal to 2. Now, as I said, now we shall prove this result by induction. I've mentioned this before in my previous part of this chapter. So somehow we have to design a suitable statement to prove it, to prove by induction. Now we need to think about what could be the P of n. So the question is, what could be P of n to be proven, to prove by induction? Now, before going into this, let us first translate the problem from one object in three-dimensional space to one about objects in the plane. So take a convex polyhedron as in the example. Let's say take a convex let's write with the same pen. Take a convex polyhedron as in the theorem and choose one face of it. Regard this face as a window. Put your eye very close to the window and draw on the window pen the vertices and the edges you can see through the window. So we will say, regard this face is a window. Put your eye very close to the window and draw on the window pen the vertices and edges you see. You can see through the window. The result is a figure in the plan with straight edges, vertices, and faces. The result is the figure in the plan with a straight line, straight edges, vertices, faces. Now, for example, here's what we draw. Here is what we would draw for the cube, the tetrahedron, and the triangular prism. Let me show you those. So okay, now these are the examples we can see that if you see through, if you follow this process and see through a cube, you will see this part, you will see this, and for a tetrahedron, you will see this, and for a triangular prism, you'll see this. So the resulting figure in the plane has vertices V, edges, and F minus 1 faces. We lose one face. The resulting figure in the plane has V vertices, E edges, F minus 1 faces. So we lose the one face since the window is no longer the face. We lose the one face since the window is no longer the face, right? So it is a connected plane graph in the sense of the following definition. So the result is the connecting plane graph. And to know that, we define a definition. Definition: a plane graph is a figure in the plane consisting of a collection of points which are known as vertices and some edges joining various pairs of these points with no two edges crossing each other. A plane graph is connected if we can get from any vertex of the graph to any other vertex by going along a path of edges in the graph. Okay. For example, the connected graph is going to be, so we have a edge so it's going to be like this. Like this. So this would be the example for the connected graph, and it has vertices, 7 vertices, 7 edges, and 1 face. Okay, let's talk about the theorem. Let's give another theorem which will help us to prove the first one. It says that if a connected graph has a vertex, his vertices is V vertices, E edges, F faces, then V minus E plus F is 1. Now, theorem 9.2 easily implies Euler's theorem 9.1. So, theorem 9.2 implies Euler's theorem 9.1 is for if we have a convex polyhedron with V vertices, E edges, and F faces, then, as explained above, we get a connected graph, plane graph with V vertices, E edges, and F minus 1 faces. If we knew 9.2 was true, if we knew that theorem 9.2 is true, then we could deduce, then we could deduce that V minus E plus F minus 1 is 1, and hence V minus E plus F is 2 is required for Euler's theorem. So we need to prove 9.2. So we need to prove theorem 9.2. And then just from there, we can induce the result. So let's give the proof. Okay. So we say that here is the statement P of n that we are going to try to prove. So we have P of n, which is every connected plane graph with n edges satisfies the formula V minus n plus F is 1. Now notice that P of n is a statement about lots of plane graphs. Lots of. Not only the one, but lots of plane graph. So P of 1 says that every connected graph with one edge satisfies the formula. So then P of 1 is every connected graph with one edge satisfies the formula there is only one such graph, that is the line. Okay, this has two vertices. This has two vertices, one edge, and 0 faces. So 2 minus 1 plus 0 is 1. Satisfies the formula. Likewise, P of 2 says that this graph says that this graph satisfies the formula, which does that this has V3 E2 F0. So that is 3 minus 2 plus 0 is 1. Okay. P of 3, there are 3 different connected plane graphs with 3 edges. There are 3 different connected plane graphs with 3 edges. So okay, 1, 2, 3. Okay, and each satisfies the formula. Each satisfies the formula. Then let us prove P of n by induction. First, P of 1 is true, is observed above. Now, assume E of n is true, which means so every connected graph with n edges satisfies the formula. We need to deduce P of n plus 1. right? So consider a connected graph G. Consider a connected graph G with n plus 1 edges, and say G has V vertices, E and F faces. We want to prove that G satisfies the formula, so we want to show that V minus n plus 1 plus F is 1. Okay. Now our strategy will be to remove a carefully chosen edge from G so as to leave a connected plane graph with only n edges and then use P of n. Okay, this is the strategy. And we can do that if G has at least one face. So say the strategy is lose one edge and remain the graph still connected. Okay. Now say if G has at least one face, i.e. f is greater than or equal to 1, we remove one edge of this face. We remove one edge of this face. The remaining graph G prime is still connected and has n edges. V vertices and f minus 1 faces. Since we are assuming that P of n is true, so since we are assuming P of n, we know that G prime satisfies the formula. Hence, V minus n plus f minus 1 is 1. Therefore, V minus n plus 1 plus f is 1 as required. Now, this was the condition. What about if G has no faces at all? At all, which means f is 0. Then it has at least one end vertex vertex that is a vertex that is joined by an edge to only one other vertex. Right? And removing this AND vertex, this vertex and its edge from G leaves a connected plane graph G double prime with V minus 1 vertices and edges and 0 faces. Then by P of n, G double prime satisfies the formula. So V minus 1 minus n plus 0 is 1. Hence, V minus n plus 1 plus 0 is 1, which is the formula for G. So we have established that P of n implies P of n plus 1. So P of n is true for all n by induction. This completes the proof of 9.2 theorem and hence Euler's theorem 9.1, because 9.2 implies the 9.1.